gonna record on this computer. I may switch screen a bit when I want to plot my graph, but otherwise I will probably stay mainly on this main screen. So I'm also joining on my iPad. Okay, so here we have a student investigating a spring supporting a wooden strip. So in question 1, right, they can give you anything. So in SPM, there was a fixed list of experiments that you can memorize. Every chapter got that few one, right? At least that was how I taught my students in SPM. Every chapter, there's a few experiments. They're hallmark experiments, but if you get them right, then you should be fine. But in this case, they're just giving you like some random scenario and random stuff to measure. Okay, and then they will tell you a long story. So to help you organize this information, generally speaking, I would suggest that you start to do a tabling process. Okay, so if you have actually attempted the paper and you want me to mark yours, or I use it as an example, that's okay, or we can do it together. All right, so I'll start with the physical quantity. Anything that is inside the equation, okay, or anything that I can think about. So the first one that I notice is it says that this end of the strip is at point P, and the strip has a length L and an angle theta. So there is L, there is theta. Spring is attached to the strip by a wire at a distance of D from the point P. Okay, so that's probably D, which needs measuring as well. And the wire is at an angle of beta to the strip. Okay, beta. So I'm saying that L and D are probably related. So I'm just going to rearrange a bit, and then theta and beta, because they are angles. It is suggested the relationship between x and theta is this. So an equation is always provided for you, okay? In a rare scenario, they can say it is suggested that x is proportional to theta square, okay? No? So in very rare cases, it could be, let's say A is proportional or inversely proportional to B square, then the equation is A is equal to KB square. Okay, but oftentimes in the more modern question, they will just give you the whole equation, where K is a spring constant. So I have K and I have W. Okay, what is W? W is just a constant. We don't know what W is. Design a laboratory experiment to test the relationship between X and theta. So this is the first one. And explain how your results can be used to determine the value of W. So for X and theta, whenever we do an experiment, it's always to find relationships, at least for physics. For other sciences, the experiment tend to be different, but for physics, it's more like, in this condition, I can set it up such that I look at the relationship between these two, which means one of these will be your manipulated and one of these will be your responding. But SPM use manipulated and responding. But if you want to use the language that Cambridge wants from you, manipulate will be replaced by independent. And responding means I'm responding to something else. So I'm dependent on that something else. Okay. So independent variable is something that the experimenter change or the student. So independently, you go and change it. And then the dependent one is the response to the change. So responding to the change. So you're dependent on the other thing. Okay. So we start with that one. Or you can say vary the independent variable and measure the dependent variable. So one of these will be X and one of these will be theta. So which one do you think, let's say pretend you're doing the experiment, which one is easier for you to change? You, the experimenter. Which one would be a suitable thing to manipulate to be the independent variable? Do you think it would be the angle theta? So I adjust the angle of the wooden strip? Or do you think it's the value of X, where X is the extension of the spring? Oh, I didn't even have X here. Okay. The angle says enough. Yeah, makes sense. So the angle is something that you can adjust, right? maybe you just move the wooden strip a bit and let the spring extend. But it's very hard for you to fix the extension of the spring. It's like, oh, I know the exact angle to put so that the spring exactly 2 cm. Very hard now. So I'm probably going to guess that this one is the independent variable. And then this one is the dependent variable. Okay. And then which one is constant? Can they all be constant? I mean, normally we just done lion is all constant, but I don't know whether you have done this experiment before, but which one should be kept constant in this case? What do you think? We have the strip is fixed. I mean, L and D is fixed, but the angle, I mean, the other angle, does it have to be constant? So if you look at all of this, right, K is a spring constant. So spring constant is already constant. W is constant. So this one question already gives, you don't have to mention. Okay. Out of these three, which one also must be constant? What do you think? Of course, L, we use the same wooden strip. This is also already constant. So I'm basically eliminating a lot of things. Okay. So which one do we need to consciously keep constant? So already constant are things like L and K. So what I mean by already constant is unless you change the spring or you go and change the wooden strip, these two things will not change. What is the thing that you have to measure to keep it, to make sure it is constant? I hope you understand the difference. There's a constant that is always the same. For example, the spring constant of the spring is always the same, unless you spoil the spring. I don't have to measure the spring constant in every single experiment. But there's something that I have to like do extra effort to keep it constant. You think it's D? Because this one is male here. So I don't think it's D, right? Okay. So the answer is beta. We keep constant. Okay. So using the list rule, recently highlighted by Cambridge, they don't want you to list down everything. So it's easy to just list down, keep constant L, D, K, W, and beta. If you do so, it's not awarded marks because you are not choosing the thing that you need to keep constant. So when we say keep constant, means you have to monitor. Because as you can imagine, when I adjust the angle of the wooden strip, maybe I accidentally also adjust beta. So I actually have to adjust the spring when I adjust the wooden strip so that beta is kept constant. Okay, thing that you need to monitor, you have to need to be aware of, monitor throughout the experiment. Okay, I think that's it. So just make sure whenever you write these things, once you can identify them, mention about how to measure them. So this one should be really straightforward because there's no high-tech instrument here. So any kind of length, we will use a ruler. Okay, theta and beta, we'll use a protractor. Space, hang on. Ruler, protractor, and probably some stuff about measuring the spring constant. You probably need to use F equal to Kx. I'm just planning the experiment. Okay, this one is independent, so probably need to measure original length because X is extension what? And final length, and then minus. All right, so I guess we're ready to begin. Okay, so to help me a bit, I'm going to carry this with me wherever I go inside the equation. All right, so I'm just gonna start here. Teacher, what diagram to draw? Well, if they give us diagram, it's a nice bonus. You can copy the diagram and then you add to that diagram. Okay, copy the diagram and then add to it. So we can do it together. Okay. So I'm just going to draw as if I'm a student. Okay. So without a ruler, because you have a ruler, you should draw better than me. So there's a strip here, and then I need to add stuff to it later. Okay, so this is my strip, and then this is my spring. Okay, so the first rule of thumb when it comes to drawing is things cannot be suspended. Nothing can float. Nothing should float. You see a ruler, draw a retort stand to clamp the ruler. You see some spring floating in mid-air, you need to secure the spring to something. And normally the support that we have is always some form of, where's my beta? Okay, now my beta is somewhere. My drawing is so horrible, but in my defense, I don't have a ruler. Okay, anyway, this is my beam thingy, my wooden rod, wooden strip. Yeah. So we probably need to secure the spring. Okay. So generally support, right, is always a clamp or a stand. So maybe I will, if you don't know how to draw, the best place is to look at your paper tree. So when nothing to do, you go window shopping lah, you flip through the paper tree and see what they normally draw. Okay. But what I'll do is I'll just draw a box at the back because I'm drawing the front view. I ain't got time to draw 3D view, right? So this is the front view of the retort stand. Okay. And then I'll just label. This is a clamp. And then I draw a retort stand at the side. It doesn't have to be accurate. The labeling is more important. And if it looks reasonably okay, then it's good enough. Because we don't really want to spend too much time here. So retort stand now. This looks like a retort stand enough for me, but if you just want to be extra careful, you just call this the retort stand. You can even label this one. This is called the boss. Boss. Okay, so must connect to a clamp. The clamp also cannot float, so it has to be on the stand. All right. This wooden strip have to label. All the main character we label. Spring, wooden strip, and also all the relevant angles. So you got theta here, you got beta here. What else do you have? I think that's it. You probably need to label L. You just need to draw ruler for L. No need lah, L never change, right? So you should measure your L before you even hang the thing there. Okay. So the question here is, does the wooden strip need anything? You also need to measure D. All the ones in black is in the original drawing, including the bench top lah. Label everything. Bench. What else do you think we should draw? Is there anything missing? Nothing can float. Should I clamp the wooden strip? What do you think? Let me know in the chat. Miss Lee, you say nothing can float ma. So I support the spring already. Do I need to support the wooden strip? Would you support the wooden strip? Yes. So enough, if we support the wooden strip, would it affect the wooden strip ability to change its angle? It would, right? And we don't want to accidentally disturb or kacau the thing that's supposed to be independent or dependent. Okay? So the only thing that is allowed to change in this experiment once the setup is done is X and theta. Everything else have to be kept the same. So if you clamp this wooden strip or you place a block here, then this will affect the equilibrium because there's like extra added forces. So we don't want any support. So once you look at nothing should float, then the second one could be nothing besides the variables. So your independent variable and your dependent variable should affect or should change throughout the experiment, which means do not add other things. Do not add any things that will affect, that will cause this. All right. So this is relevant to the experiment. What is not that relevant to the experiment is the idea of plumb line or support. So nothing should float, meaning they should be supported, but nothing besides the variable can change the experiment. Number 3, right? If needed, especially if we want to measure things, we can add plumb line, fiducial marker on the drawing lah, circuit. Sometimes it's a circuit experiment, not this one, okay? Spirit level, if needed lah. Don't go and just draw everything. There was once a student just randomly draw a circuit in an experiment that looks a bit like this. And I'm like, why do you draw a circuit? I don't know, miss, you always draw circuit, so I also draw a circuit then. Like, okay, teacher, do I need to draw a protractor? Not really, because we can always just, you can add the protractor here, but I prefer writing lah. All right. I guess you want the camera. So I actually want 2 protractor. I want one here. You need to draw nicely. You just draw like half a circle, then you label lor. Protractor. Probably need another one here as well. Protractor. But because you are only going to use black, right? So if you make it too cluttered, the whole thing will look like this. How to draw plumb line, fiducial marker, spirit level. Okay, that one I thought later. We finish this one first. I think this one may have to draw later. Okay, so we're going to write about the variables first. So always start with PMAD. Think about the acronym PMAD. Okay, so the first P is for defining the problem. Bring the keyboard back. Defining the problem. So this is the P. And defining the problem here just means state variables. So your sentence could be something along the lines where either you itemize it, point number 1, the independent variable is theta. Theta is one? No. Where is my theta? There we go. I'm using a Greek keyboard. Okay, the independent variable is theta, and the dependent.
Sorry, Miss Lee, just to confirm, so we can let the wooden strip float?
It is not actually floating because from the perspective of the strip, right? We can let it float because number 1, there's a force here, tension, and then there's a combination of normal force and friction to keep it from sliding, and also the weight of the strip itself. So this thing is in equilibrium. And we can also let it float because if I go and let's say add a block here to support it, then what I'm introducing is a third force. And I'm trying to study the relationship between this theta and the tension in the spring, which is represented by the extension. So if I were to add something there, either by putting a block or maybe clamping it down with a retort stand, maybe I can add a clamp here, what will happen is it will affect all the experiment. Does that make sense? Adding a clamp or your hand or anything would affect the experiment. So although nothing should float, nothing should also accidentally change the experiment, which is the second point. So don't add anything, even if it's support, that can cause this, that can cause the change. So this is In other words, make sure your support don't disturb your experiment. Whatever support you added doesn't affect experiment.
Okay.
Okay. Support wrongly. Yep. Of course, if you accidentally added one, then 1 mark will be deducted. It's just 1 mark. The diagram is 1 mark. Okay, so the dependent variable is x. Okay, or you could write vary theta, measure x. Measure x. All right, then we will keep the angle beta constant. I have beta. Yes. Okay. Next, we look at the method. Just what method? You can also itemize it. It can be point form. It can be 1, 2, 3. Doesn't really matter. Physics people very chill one. Anything also can. So we start the experiment. Meaning when we start the experiment, you can always just help your brain a bit by just writing an introduction sentence. So experiment is set up as shown in diagram. Okay, but the method here is basically to try to answer the question of how did we measure all the things that we need to measure? How to measure? The defining the problem is what to measure. Okay, so this one is just right to warm up. So now what do we need to measure? So that's why we list down everything because scared forget ma. Look at the side here. To help you see better, I will highlight the text. Okay, so first thing I see is L and D. So L and D is measured using a meter rule. That's all. Yeah, that's all. No problem. Okay, next. You can also say something along the lines of theta. So I'll say theta. Change my theta. Is measured using a protractor. Okay. What else do we need to measure? Ruler, protractor, X. Okay, so I would say it's measured using the protractor and the original length of the spring. Maybe you want to call this L0 or X0. I'm just going to call it L0. You can call it whatever you want. Of course, I'm going to write this in the equation later. So it depends on what equation you choose to write. I'm not sure what happened there. I shall just press enter. So the original length is measured using a ruler. Okay, then final length of the spring once the wooden rod, we call it a wooden rod, wooden strip is in equilibrium or stops moving. Because when you hang it, it will oscillate a bit, right? Again, using a ruler. I think you write once is enough already, but you just make it a habit of whenever you want to measure something, you just make a note, use this to measure that. L. Then number 6, you can then say the extension of the spring X is equal to L minus L naught. Okay. You can be fancy, like you don't want to use ruler, you can use calipers because the spring is normally like 4-5 cm in the lab. But that is provided you know the spring. If not, then this is fine. There we go. Okay, so we need to talk a little bit about beta. So make sure that the retort stand and clamp is adjusted to keep beta constant. So for example, when I change theta and then beta change liao, what I will do is I'm going to scroll up for a bit. So if let's say I change the angle of theta, beta would change also, right? So what I need to do is I need to change the height of this boss, adjust the height of the clamp, bring it lower or higher. Okay. Okay. You don't necessarily need to say. If you say you don't know how to adjust it, you just say adjust the retort stand and can keep beta constant. It's okay to be vague here. All right, so let's do a roll call. So okay, about L. Anything else extra you want to say about L? L is very straightforward. You just put it on a ruler and you measure. It's fine. Okay. D. D is kept constant. So I'm just going to make sure that the spring is always attached to the same, because sometimes maybe they use blue tack and then the blue tack will loosen, right? Or a tape. So the spring is always attached to the same point on the wooden strip to keep D constant. Study goes now, we mentioned everything. Okay, theta already talked, not too much else to say. Theta, beta also mentioned already, especially this part here. Keep beta constant by adjusting the report. Okay. I guess that's it. Oh wait, we have K. All right, talk about K. How to measure K? Nah, teacher, F equal KX. Yeah. So I will say hang a known mass on the spring. Okay, known masses on the spring. And I plot force against or weight of the mass, weight of the masses against distance graph. Distance, no, extension graph. So basically what I'm telling them is go after or before the experiment, go and plot the graph of mg against x for the spring. So for a few different value of m, get a few different extension and draw the graph. Pass through the origin, please. There you go. Okay. So once you can hang the known mass from this graph, I can find the spring constant. The spring constant K is measured or is calculated, or it's just equal to the gradient of the weight extension graph. Interesting, right? I follow this topic. So how much detail do you think you need to write? Not a lot, but at least in brief sentences, tell them this is how you can do the experiment. You don't have to write another experiment inside an experiment, okay? You just need to tell them, well, to find K, I will need mg to divide by x. But that will give you 1 mark. It will be better if you just mention, for different weights, plot a weight against extension graph. Okay. You can even say by measuring each extension since our space here. Okay, I think we've done the list already for M. If there's anything missing or you thought of something, you can always add in the done line additional detail. Okay, so we'll leave some for that additional detail. We're going to go to A, analysis, PMAD. So analysis here is, I already have data. What to do with the data? Or rather, basically, what graph to plot lah. To achieve the purpose of the experiment. So this experiment is very weird one. In CIE's design experiment, I like how they just bypass the whole hypothesis section. So you don't really need to make hypothesis, you just need to design an experiment. So how do I know the relationship between theta and x? I need to plot a graph. So I need to copy the equation. I'm going to transfer the equation over, okay? Oh, I guess put it down here then. Okay. If I zoom in that much, the lag is, when I move stuff, it's just extreme. Okay. So you can always leave space here so that you can add more stuff later also can, no problem. Got more than enough space. Provided you write, don't write essays, okay? Point form is good enough. So I graph to plot, you can start from the equation. And then I think to myself, my variables are theta and x. And I want a straight line. So the best way to get a straight line is actually to rearrange this. And this is cos theta will be equal to k d sine beta times 2 divided by WL. Whole thing times x. Okay. So you could plot this cos theta against x. Because don't forget, you must have, it has to be one variable on one axis, the other variable on the other axis. So your variables are theta and x. Teacher, can I plot x against cos theta? Can. Can I plot cos theta against x? Can. Are they very picky about this? Not really. No. As long as straight line. So I am committed, I already arranged. So I can then say, number 1, plot a graph of cos theta against x. Number 2, remember we have two purposes. One is to test the relationship. So relationship is valid if the graph is a straight line through the origin. The through the origin is compulsory, okay? Not any straight line, but the graph is supposed to be like that. Now, the only difference between these two graphs is gradient. This gradient is 2kd sine beta over WL. And this gradient terbalik ma, so WL over 2kd sine beta. Gradient. Whichever lah, straight line can already. Straight line through the origin. Okay. So now we need to find W. So purpose 1 is done. Make sure that you can test the relationship. Purpose 2, find W. So you can say that the gradient of the graph in number 2, or on the graph of cos theta against x. Let's say I call the gradient m lah, because nobody use m here. M is equal to 2kd sine beta over WL. Hence, W is equal to 2kd sine beta divided by L times M, or L times gradient. So the mark scheme like to leave the gradient out as a separate thing, which is okay, because you're only ever going to write it one time. But you can also put M, provided you already define what M is here. This part I already defined. Oh, gradient of the graph is M. Then you can use M. Or you just want it to look at the mark scheme so that the examiner can progress quickly and just write gradient. Okay, we are done. We have achieved the purpose. You can stop here. Or maybe you can write some additional details. The done line, the any other business. All right. So the first thing we write is safety lah. Safety is quite standard, right? Always have safety. All right. Any idea what you would write for safety in this experiment? What are the possible things that can be dangerous? Please don't tell me wear gloves. Nothing will be hot here. Or electrocute yourself. There's nothing here to electrocute you. What should we do? How do we keep ourselves safe? What are the possible accidents that can happen? Now, if you forget the setup already, I draw for you. I let you see the setup is here. What are possible accidents? Always got safety one for that 1 mark. The spring fly. Fly. What causes the spring to be dangerous when the spring fly? Which part of the body you don't want it to hit? Ideally, the eyes. Very good. Wear goggles. Okay. So I'll say, because your eyes is the most, I don't want to say the eye is the most precious part of your head, but actually your entire head is very precious lah, okay? But wear goggles. Okay. No, your head not precious, man. Very precious, huh? Wear goggles. Don't just say wear goggles. Full stop. Cannot. Must explain why. So always, when this additional detail, always explain why. Why do you write this thing? Wear goggles to protect the eye or to prevent the spring. Can I write flying into my eye? I can. Or you can say recoiling into eyes. Forget now. Let me go back to my picture. If you do this experiment, and let's say your wooden strip is quite berat lah, maybe you use kayu jati, rainforest. If this is very heavy, the protractor can actually, the bench can actually move. Not bench, sorry, the retort stand. So you may actually want to add a G-clamp here. Teacher, how to draw G-clamp? It doesn't really matter. It looks like a G-clamp can already. Then you label G-clamp. Looks like a G-clamp. It works. It's science. The label matters. You don't label, even if it looks like a perfect G-clamp, I can choose to not give you mark because I don't know what you're drawing. All right. So you can remember to clamp this. Or you could also mention here, because things can drop, right? Flying things or dropping things. You can say clamp the retort stand. To prevent it from slipping on the bench. Sliding on the bench. or toppling over. All right, number 2. So since we didn't mention, I would say use the same wooden strip, D constant, by using same wooden strip. Okay, number 3. So it's all just done line one. Things that you think is maybe important, let me just write. Okay, maybe we need to talk about like how this system, this point P here, this was point P, right? This point P can actually like move around because there's friction, but also at the same time, this friction, right, got 2 types. One, if you study further mechanics, you will know there's a static friction and then the kinetic friction. So we basically don't want this point P to move lah, if can. Because again, we only care about this and theta. The rest we just like whatever. So I don't really care about the friction as long as my wooden strip doesn't move. So I don't want it to move. Clamp is not the idea because we don't want it to exert extra force. So what I could say is, I could say to prevent the strip from sliding at point P, use blue tack, I like to call it adhesive putty, because blue tack is a brand. Liquid paper is a brand, but it's actually correction fluid. Starbucks is a brand, but actually it's coffee. Pampers is a brand, but actually is diapers. Okay, so you can say, I think you put blue tack is fine, but the actual term is adhesive putty, okay lah, something to stick it there lah, or a hinge. Okay, we need to keep P rotating because P have to change angle, right? To ensure P is able to rotate freely, to vary or to change theta. Okay, because we're changing theta. Okay, how can we attach the spring on the strip? If you go back to this one, now the spring is here. How to lekatkan that side? And then here got wire. Oh, sorry, they forgot to label the wire. Okay. How do I attach the wire to the wooden strip? What would you suggest? Can I use the adhesive putty again? You can, but the adhesive may not be strong enough, generally speaking, because we have no information about how heavy the wooden strip is. Okay, so what we could say is we would maybe drill a hole, wooden mount on the wooden strip, and tie the wire, or you could say use and it's a very strong tape to stick or to secure the wire on the strip. Okay, now the time that you've been waiting for, fiducial markers. So fiducial markers in general, okay, I show you how it looks. I asked my friend Google. Fiducial marker is just a pendulum to show you where up down is. Okay, this is the Wikipedia definition of fiducial marker, which is correct. An object placed in the view of an imaging system. You are the imaging system right now because you are using your eyes to measure, right? Use your eyes to take measurement. You use your eye to read the protractor. You use your eye to read the ruler. Okay, and it's used as a point of reference or a measuring position. So mainly the point here is fiducial marker is a reference point. It's used as a point of reference. So example, let's say I have this curve track, very popular oscillation question. And I ask you to time the period of oscillation. So maybe you drop the ball here and then the ball is going to oscillate front and back. Okay. A fiducial marker can be placed at the bottom position so that whenever the ball passes this marker, you will count one oscillation or half an oscillation, depending on how you count. So I will start my stopwatch when the ball passes the marker, allow the ball to go up, come down, and go back again. When it passes through the marker the second time in the same direction, I stop my stopwatch. It's like something to indicate your reference point. And for our Muslim friends, it's like a qiblat lah. It's to show you the direction. So right when you measure something in any experiment, we would like a reference point. You know, it's like whenever you're lost, let's say you exam, whenever you're lost, your eye will go to the chief examiner. That is your fiducial marker. So where do we place our fiducial marker here? We use fiducial markers. Normally it is used whenever we measure things that are suspended. So if they are like suspended, if I want to measure my phone, it's very easy. I take my ruler beside the phone, I measure. But if let's say my phone is like being hung, like I keep my phone this way, and then I want to measure the angle between my phone and my horizontal line, then I probably need a fiducial marker. So I can use a fiducial marker by finding out where the vertical is. So examples of fiducial markers. This one is also somewhat suspended now. Okay, or to time oscillation. Okay. Examples of this is pendulums. Okay, this one is you can use this to determine the vertical axis. For the oscillation one, I can probably use tape. So it can be anything, it can be a tape. Anything that doesn't kacau the movement of the ball will work. Okay. So which one is suspended that we measure that probably needs some fiducial marker? It's like hanging halfway, neither here nor there one. For example, do you think it's hard to measure theta? Do you think theta needs a marker? No need, teacher. I just put on the table, then I measure the position of the wooden strip. Okay. What about extension? How do you actually measure your extension? You're going to put your ruler like this. Right? Example, you're going to put your ruler. But it's very hard to angle your ruler properly. There's no reference point. So what I would normally suggest is to place a fiducial marker, tie one pendulum here, tie another pendulum at the end of the wire, because as the spring extends, this pendulum 1 and pendulum 2 will move, right? Okay. then what you can do is you measure the distance between here to here. So now you are not measuring the spring or disturbing the spring. Let me label the pendulum first. These are your fiducial markers. These are all just bold extra points. You don't write, you can still get full mark. It's just extra stuff. This question maximum can get this is maximum 15, right? Can get 19. So you don't draw this one, you can still get 15 out of 15. Teacher, if I get 19 out of 15, then it's still 15 out of 15. So don't worry too much about this. Then you can measure the extension, the length here, this is L. So it's easier to measure the ruler, if that makes sense. You just need to angle the ruler such that the scale on the ruler is parallel to the marker. There, your ruler got this line mark. So when you measure, you just need to make sure that the fiducial marker is parallel to the scale. Then this is your L already. Okay. But it's not very fixed. Okay, spirit level is not needed for this experiment, but if let's say you are looking at a certain experiment that needs spirit level, for example, you want to make sure that this clamp is perfectly horizontal, example, not needed here. You can just draw a spirit level like this, okay? And then just label spirit level. I will show you a few examples of this in pictures. So, walaupun tak never use IRL, but at least you've seen it before. Lazada has been pushing a lot of their ads. I'm getting so many ads from Lazada. Am I your target group? I am not your target group, you know? Okay, anyway. This is quite an interesting experiment, but it's basically an inclined plane with an object there. And I want you to see that this thing will slide upwards. There we go. This is a spirit level. Okay. So when this thing is, when the bubble is in the middle, it means that it's perfectly flat. So he is showing us that this thing is at an incline, so the bubble is on top, showing that this side or this side is higher than the other side, so the bubble will shift. If this is perfectly flat, the edges of the bubble will touch these two lines. So normally, I just draw this one long. I'm not going to draw the whole thing, but yeah, very cool, right? If let's say, okay, you can see if they put this normal cylinder, this cylinder will slide down, but the other one will slide up. Now if they switch position, equilibrium, okay lah, not in syllabus. But think about why. I mean, you can watch the video later. I think he explains it quite okay. But yes, this is your fiducial, this is your spirit level. I just put this here for you. Okay. This spirit level is placed on horizontal surface to make sure it's horizontal. To ensure perfect flatness. So if for whatever reason you really important the experiment for your clamp to be perfectly horizontal, then add a spirit level on top. Although technically speaking, this experiment is not needed. Let me see if there are any. Yeah, all the fiducial markers that they use is actually quite meh. Like for example, this one, the marker that they use is actually a stick that they stick on the ruler, a toothpick that they stick on the ruler. Okay, lor. Sometimes your fiducial marker can be, okay, this one is a stick. Or they will place a nail here. This nail becomes your marker. So it's just a reference marker, something that you can put there at the center of your oscillation to make sure that is your horizontal. Okay. Or vertical, we will hang a pendulum. So this vertical pendulum becomes your fiducial marker between the two objects. That's all. You don't even need to draw. You can just mention the fiducial marker is tied on the spring. I write here for you. If you don't really know how to draw, or if you know what to write, sentences are, you can also use sentences. Or if let's say your diagram, there's no space. So you can say fiducial markers are placed on both ends of a spring when measuring. Actually, you can just tie it and leave it there. That can, yep, scan already. Okay, this is a 19 out of 15 mark essay. So when you open that Cal resource folder that hopefully you've been using, you will reach this part where there's key file experiment and design. Okay, so I've done a previous crash course, it's recorded, nothing much has changed. But if you go to set A part 1, this will come up for you. And here, right, will actually show you the different experiments. For example, if let's say you want to figure out how to measure vertical height, length of the spring, moving things. So these are additional details that you can write. And if you want to see how it's being implemented, you can look at that example. I will add the more recent years, but I think it's updated to May, June 20. Okay, so everything is measured. There is height, there's length, diameter, mass, time, period, voltage, how kind of circuit you want to draw, temperature, pressure, force, density, everything is here. This is a summary list of the things that they have asked before. And they can always ask again. And they can ask more than this. But if you know how to measure the physical quantity, then you are not that worried. Because it's a bit like going to choose, I don't know, choose your own, go buffet, choose your own food. So they will choose some of this. Like in this experiment, we measured length and height, okay? Spring. So there's no movement involved. We did use a marker. Oh yeah, I didn't mention average because if you want to, you can. Safety goggles to prevent injury from ice. Yeah, not bad. You write all this, probably okay already. What else did we measure? Oh, we measure angle. Do I have an angle here? I hope I do. There, protractor. If you want to, you can use trigger identity. Plumb line is a fiducial marker. So I'm going to add that there. Okay. And especially if it cannot be measured directly. So for example, this cannot be measured directly is when you use equations like d sine theta is m lambda when there's light. For light, there's no direct measurement for angle. But for this one, I think it's measurable. So you just have to update your your software if you don't know how to measure certain physical quantities. If you want to write repeat experiment, I'll be a bit careful. So here's what I'll say. What are we measuring? The repeat experiment always have to talk about the dependent variable. So repeat measurements of X for each particular or the same theta and average. So your sentence should be repeat measurements of the dependent variable, okay, for the same independent variable and average. So you can write average. Actually, this is the same 2D1 mark lah. Or you could just always write the same thing, but don't write repeat measurement for dependent variable. No. Follow the experiment. So if the experiment say X is my dependent variable, then repeat measurements for the dependent variable for each same theta or for same values of theta and average. Okay. So after this, it's just you grinding to make sure that you are relevant, you are suitably confident that whatever they throw at you, you can also do that. Let me take a peek on the ON21, the other variant. This is phi 2. So as a practice, you can look at phi 1. But phi 1 is a totally different experiment. This is standing wave. Oh. So we are measuring very different stuff already. How do we know there's standing wave? This is actually an easier experiment because you have studied this before. Although I would argue you have also studied the other one in equilibrium, but that's not the important point here. Your variables would be F and D, which is the frequency of the sound when I get a stationary wave pattern. But in this case, I can't see the pattern. What do I need to draw? Maybe a loudspeaker, maybe a reflector, throw back to AS. So you've got to figure out how to measure F and D. Measure F and D. L can be measured using a ruler. Go and try. A number of different tubes available. This is such a big hint that your D becomes your independent variable. D a diameter? Yes. Okay, so just go and you just once a day, you spend 10 minutes just planning out the experiment. The important thing about the experiment is, I mean, if you can reasonably write, is to sketch the diagram and then also roughly know how to measure everything, build this table. If you can build a table and you are relevantly confident that you can extrapolate, it should be fine. Yeah, generally, it's fairly easy to get at least 12 out of 50, even if you tend to miss out a lot of points in the additional details. Okay, that's question 1. I'll throw it inside your Google Drive. Okay. You can look at question 2 now. Anyway, if you want a template for question 1, it's also here. I think it's in part 1. I mean, there are actually a few versions of the template here. So you could always use it. But it's basically just me repeating myself, but in point form. So I think you'll be fine. Okay. If you want to have like very specific examples, this tool set that I gather is more or less enough already. And then I think later what I'll do is as you practice, I will tell you which past year I collected it from. Okay. So whatever that is recorded on the channel is dump here one. So I've recorded FM because FM19 was a anomalous, difficult paper. Like I don't know why that paper is hard. Board question also very hard. So unless it's like it's a very savage paper. But otherwise, most papers are just quite predictable. Like a reasonably prepared student should be able to do. Okay, so do you want me to do another question one, or would you like me to carry on with question two? What do you want? Maybe I'll do a poll, but then you can carry on. Okay. Nice. So the focus of question one is measuring stuff. And the focus on question two is actually to handle data. So I think okay. So I'm going to share content from my iPad now. Okay. Testing, can still hear me, right? Okay, I think still can. Okay, very nice. Kadang-kadang cannot hear. Later when we learn astro, I can let you look at stars. Oh, give me a sec. We are Monday. No, today is not Monday. Wait, the sync needs a bit of time, but we will get there. There we go. Okay, so for this question, right, the focus is DP, SF, and graph. DP, sigfig, graph, and uncertainties. So if your strength is on calculation, then it is something that I will go for lah. Because I'm better at calculation than writing essay anytime. All right. That's why my essay technique also looks a lot like calculation at the steps. So for this one, they will again tell you a story that you may or may not know, you may or may not see before. Here, there's a Geiger-Müller tube that can detect beta radiation. Your radioactive source is here. Okay. And the student places a paper between the radioactive source, assuming to block some of the beta particles. GM tube is connected to a rate meter, which records the count rate. I don't think we have covered this chapter yet, but count rate is simply, or to oversimplify it, is the number of decay nucleus, or I guess in this case, beta particle, because each decay nucleus will release a beta particle per unit time. That's why there's a rate here. Okay. The thickness T of the paper is measured in two different places using a micrometer. Interesting idea. Two different places, micrometer. Student repeats the experiment for different thicknesses of paper. Okay, it is suggested that R and T is related by this equation, where R0 is the count rate without any paper, and mu is a constant. So if you remember X-ray, right, this format is very, very similar. Okay, this is hopefully not a new equation. So a graph is plotted of ln R on the y-axis and T, which is the thickness of the cardboard or the paper, on the x-axis. Determine expressions for gradient and y-intercept. Every question starts the same. They give you an equation, linearize the graph. So the first skill that they test is, are you able to linearize y equal mx plus c? If the first skill got problem, there are videos in the playlist. You probably need more practice for. Because if you cannot find, or you don't know how to linearize the graph, then you cannot start the question. I mean, you can still do it, but a lot of marks will be lost. So right now, they help us by saying we want ln r, so just ln both sides. Ln r is ln r naught e negative mu t. So I see that there are two, there's r naught, and there is this whole thing here. So I can separate them, right? Ln r naught plus ln e to the power of negative mu t. Okay, so the identity that I'm using now is ln AB bracket is ln A plus ln B. Okay, so let me continue rearranging. So I can have T. Ln E is 1. So this is 1. And then I can bring down the negative mu T. I'll bring this down first. Negative mu T ln E. And this is ln R naught. And then at the end of the day, we have ln R is equal to negative mu T. Ln E is 1 plus ln R naught. So certain people, very big brain one. They don't need to do that many steps. If you're actually very familiar with the equation, here itself, you already, like somewhere in the middle, you already know what you need to do. But if not, then you can always compare your good old y equal to mx plus c. This is your y-axis. Okay. This is your x-axis, in this case, your t-axis. So your gradient m will be equal to negative mu, and your y-intercept is ln r naught. Correct, then get 1 mark. Wrong, then 0. Pretty straightforward. All right. This one is okay, no problem. We move on. Okay. So now you are given basically the average, the two thickness, because we repeat the thickness measurement of the cardboard using the micrometer twice at different position. So you are asked to record the values of average and ln this and include absolute uncertainties in average t, which means this one should be t plus minus uncertainty in t. Okay. So we'll do it now together. I guess we can compare answers. Mm-hmm. Mm-hmm. Think about the uncertainty. How to write uncertainty for this? Because normally they will put uncertainty here, so it's not a bit anomalous. How to handle this uncertainty? I'm gonna sidetrack and talk about uncertainty, but what are your thoughts? Okay, I think the average is clear enough. So sidebar a bit, literally sidebar. When looking at uncertainties, there are a few scenarios that can happen. Number one is a fail safe, meaning all the time can use. Always can use, which is half times the range method. For example, we go back here. What is the range of T1 and T2? Sure, the range for each reading is different. Yeah lah. So the absolute uncertainty for each reading also different. Interesting. Okay, so what is the range for this one? This one, the range is 0.06, right? Because 0.19 minus 0.13. I write the first one for you. 0.19 minus 0.13 is 0.06. So if I repeat, this is 0.06, 0.04, 0.04, 0.04, 0.04, 0.04. So half the range times half. So this means this one would be 0.03, 0.03, 0.02. So this one sentiasa boleh pakai. But sometimes the calculation is very convoluted, meaning you need to square and then divide by something else, and then I don't know, log or ln or do some weird things. Then using identities can be faster. But if you're like I don't want to think so much, then you slowly find the range. This range is easy to find. If you later, I'll show you some examples where the range is just that. Okay, so can always use is half the range method. Okay, but I will add an asterisk here. Be aware of fractions. Okay, what I mean is, e.g., if let's say I want to find the uncertainty of A over B. I say A over B is a certain ratio lah. I'm not sure what ratio A over B is, but okay, whatever ratio A over B can be. So let's say, and then you have a table of values for A and a table of values for B. So the A over B maximum is actually to take the smallest value, sorry, the largest value of A max, divided by the smallest value of B. So you take a large number divided by a small number to get the largest possible number. Right? So for example, maybe I say A is equal to 24 plus minus 2, and B is equal to 4 plus minus 0.5, 4.0. So if I want A over B maximum, I will have to take 26 over 3.5. Because the smallest possible value for B is 4 minus 0.5. And the largest possible value for A is 24 plus 2. (4.0) minus 0.5. Then only you get the maximum value lor. And then if you want to find A over B minimum, then it would be A minimum over B maximum. So you will need to take 22 divided by 4.5. So let's just do this as an exercise. So it's 26 divided by 3.5. So this one is 7 point. Okay, about SF, right? Everything is 2SF. So I will stick to 2SF. This is 7.4. And 22 divided by 4.5. Wow, 4.88888. 4.8. So hence, it's a lot of work because first you need to make sure you calculate the max and min correctly. Hence, half the range of A over B is equal to half bracket 7.4 minus 4.8. No, wait, 4.9. Because what did I round? Do not round prematurely. 7.4 minus 4.9 divide by 2, 1.25, which is 1, because you write this in 1s. Okay, hence A over B is equal to 24 over 4, which is 6. So A over B plus minus uncertainty of A over B is 6 plus minus 1. You do so much work for the plus minus 1. So sometimes half the range method, whenever there's other calculation that is not this straightforward, like finding the average, then you have to slowly do, which will eat up some of your time. It's not complicated. It's just trivial. You need to find the max, you need to find the mean, you need to find half the range, then you put it in. Or number two, method number two, I will use identities. There's probably some of you whose brain is screaming, teacher, use identities, correct lor. So if I know A is equal to 24 plus minus 2, and B is equal to 4.0 plus minus 0.5. A over B is 24 over 4, which is 6.0, because we're going to stick to 2SF. And then the uncertainty, we've done this in AS before, uncertainty of A over B will be uncertainty of A over A plus uncertainty in B over B. So it's the percentage uncertainty. This is divided by A. So the uncertainty of A over B will be equal to 2 over 24 plus 0.5 over 4.0. And the whole thing multiplied by A over B, which is 6. So hopefully this one is just a regular AS situation for you and you have not forgotten this. But this is still 1.25. Of course, you don't have to ask to know my preference, right? It's not a lot to calculate. Why I do this to myself? And I cannot show any of the calculation on the table. So I have no space to write also. And I'm not allowed to bring any scribbling paper. So I'm stuck with that few pages that Cambridge gives me. I'm just going to use identities unless I don't know the identity. So identity is what I will call a shortcut method. So preferred because it saves you a lot of time and it's faster lah. Like I think this is faster, one is one SM. So that's why your A over B is already back to 6 plus minus 1. Preferred because oops, spelling preferred not called. Okay lah, this is a shortcut. So if you know the identities, that will be great. But if you don't know the identities, I will include them now for you. 1 sec. The half range method is always nice, provided I mentioned before, you know what is going on lah. Okay, and it can always be used. So if let's say they give you some strange identity that you don't know, then use half the range lor. Let me paste it in on my desktop. So just a reminder, just want to put it all at one place for you. Okay, so here are common uncertainty identities. Okay, as you can tell, we have used the second one, number 2. Okay, number 3 is also not unknown. And then if it's for log or ln, we're going to use the identity of uncertainty in ln x is equal to uncertainty in x. Uncertainty in log base 10 or log base ax will be 1 over ln 10 uncertainty in x over x. The derivation is recorded in the formal playlist. So if you're interested in the derivation, it's just some calculus or just memorize law, or even better, what's that word for it? Use the min max method. Okay. So sometimes you are forced to use the min max method because they didn't give you any uncertainty. They just give you 2 readings. So these are the cases where you have no choice. But other times, uncertainty, identities can be used. Okay, so I'll just park everything here for you. So this is an example of how you can always use, and then identities is normally the faster way, less things to write, whether you know what to write lah. Okay, we follow, continue. Next. Well, we are not asked to find the uncertainty of ln R because we don't even have uncertainties for R in the first place. So I'm just going to cautiously remind you that ln is a special case. Normally, for all other values, is follow sig fig or +1. So for example, 2SF, 2SF, 2SF. Can write 3? Can. But this is not possible, okay? Or 3SF. If relevant, in this case, it's not. Okay? But exception here, ln or log. The values will be from SF transfer to DP. Whereas for the previous one, this one is SF follow SF. The other one is value is SF follow DP. If you want to know why, it's because the number in front, for example, this one is 3SF. So by the time I reach here, it should be 3DP or 4DP. Okay. So let's say I write to 3DP. This is 3.SF. 3DP, yeah. So this will be 3.865. Because what is significant or meaningful to your log and ln is not the first number. Not that the first number has no meaning, but the first number just simply tells you that your exponent is to the power of 3. What is important is at the back. So because we don't learn the log scale in your physics or your maths, we've been drawing just normal linear graph. So you don't really get it. But it's a bit like the number in front has no meaning. Everything that you calculate here is going to be 3 point something. So you can either write 3.865 or 3.8649. But I'll stick to less SF. Less SF is easier to plot. And I am team easy to plot graph. Just don't want. Well, but they are both okay. So for any calculation, you square, you divide by 2, you average, you ratio, you times 10, doesn't really matter. From here to here, SF to SF. But if let's say you are doing log and ln, then it is SF to DP. This is the only case. Okay, so it's because only these numbers are significant from the perspective of log. 3 just means, this is ln, so 3 just means e to the power of 3. But what is behind is the one that gives you meaning to the root. Okay. So an easier way to understand this whole meaning thing is to use log base 10. So for example, if I log base 10, 110, and then I log base 10, 170, because this will all be 2 point something, because it's 10 to the power of 2. So this 2 point something doesn't really give me information about the precision of the data. This one is the one that we want. The 2 point something here is just for 10 to the power. So that's why we just choose to look at the DP. Okay, so this is 3SF. So this should be 3DP, 3DP, or 4. Okay, we can continue now. So this will be 3.689. Is it? Oh no, 44. What do? 784. Then 3.642. 3.391. Okay. All right. If they want absolute uncertainty, then they need to give you some plus minus and back. But in this case, it's not needed. Okay, no? Your table is done. So the marks, right, would be if you calculate these two rows correctly, you get 1 mark. Then if you calculate all this uncertainty correctly, you get another mark. And now we need to plot a graph of ln R against T. Include error bars. Draw the line of best fit and find the gradient and include the absolute uncertainty. Everything here on out is standard. Okay, so I'm going to plot a graph. I guess if you have your graph paper, you plot with me. But the reason why I need double screen, I'll try my best. You plot. So if let's say you are drawing your own graph paper, you may actually need to copy the axis yourself because the axis is always given. The focus of the graph, this question is not to see whether you can determine the axis or not. So follow the axis that is given. 0.16, 3.864. I kind of pull up the table on my other screen. Okay, you plot there. I plot on my PC because I can zoom in more. Oh, liao lah. 1.6 is here. Okay, I'll leave the table here for you and me. Okay. 0.16. So once again, just a quick reminder, we are plotting corners only, okay? Corner plots. Make sure the plots are not too big. Oh. Okay, so you can probably see the plotted points. I'm going to zoom in on one, which is the first one. Okay. Strangely, it looks a bit better on the screen, but never mind, maybe it's an iPad limitation. So you are also asked to draw the error bar. And the error bar in this case, if you check the table, it is the t-axis, horizontal. So error bars can be horizontal, it can also be vertical. Okay, so don't get it into your brain that, oh, error bar must be a certain orientation. In this case, it's 0.03 for the first one, and then 0.02 for all the rest. So it makes it quite easy to draw. 0.03 is 3 boxes, left and right. So what we need is to use a pencil. I hope you're using a pencil. Okay. And extend 3 boxes, preferably with a ruler. Maybe I can use a very funny one. I use ruler on my iPad, but it's going to be very weird. Okay, I'll draw the first one. You can top up the rest. I'm going to switch app a bit so that I can use ruler. So start your error bar 0.03 to the left, 0.03 to the right. Okay. Your graph will be looking something like this. With a ruler, do not use freehand like me. Freehand is the best place for me to minus mark. Never use ruler. I don't need to check already. 0. Okay. I'm going to see if I can change the app so I can use a different ruler. You focus on drawing the error bar. Okay. If the value is 0.642, yes, please plot 0.64. Plot to the nearest corner. Yeah, plot to the nearest corner. Okay, I have given up on the iPad. So back to the good old drag and pull. I think because of your SPM background, best fit line shouldn't be a weakness, but I do find it quite a weakness in your IG friends, which, not gonna lie, puts you at a slight advantage. So I'm just gonna do things that I can't do in the actual paper, which is to copy paste lines and move things around as if I have a PC. One day when I free, I will figure that thing out. Today is not the day. So make sure you limit this. Okay, repeat again for the next few ones. This one is 0.02, so it's 4 boxes, 2 boxes to the left and 2 boxes to the right. Drawing lines. Graph is a 0 out of 10 experience. So don't be like me. Always end your error bar. I'll do it once I'm done with all of this. And then you can try to find your best fit line. So you can see I have plotted it all at the corners. Corner. I round everything lah. Like 3.456, I round to 3.45, 3.46. The corner, 3.4. It's 3.455. 455 is closer than 46. Let me see. When rounding, this one was rounded. I'm going to change color. This one on the plot was rounded to 3.455. This one, no problem. This one, I plot 3.640. This one, I plot 3.785. You get the idea? The nearest corner. This one, no problem. This one, I plot 3.390. Because every box is 0.005. And this one I can plot exactly 865. So no problem. This was what I plot. So you round to the near. So it's not a matter of rounding up or rounding down. Like for example, this one I round down a bit because 3.456 is very close to 3.455. And this one I round up because 3.846 is closer to 3.845. Just like 3.642 is closer to 3.640 compared to 3.645. If it's Jun in the middle, in this case, it's not relevant now. But in case it's betul-betul in the middle, then doesn't matter. Just round to the nearest corner. Okay, I'm going to draw my line now. I'm going to do this trick that I can only do here. But you use, hopefully you're using the proper method. You print it out, just draw your line. I do this one. So I get to actually zoom out and look at the whole graphic, which is something that you should do as well. English. For adjustment. Until you think the points are like somewhat balanced, and you are close to the all points. Make sure the line is long. So extend from end to end.
Miss Lee, are they like
Yep.
very strict about the line? Because mine looks kind of different because I went through like the second and the fourth points. So if it's a
I
bit
don't think
off.
mine is the correct one either. I'm trying to adjust. It's kind of hard without a ruler. Where is yours?
I don't know, mine went through the second and the fourth points.
Second and the fourth point. Okay, I'll follow yours.
But I don't
What is
know.
this one, right? Never mind, I'll follow yours. Yay! Copy friend answer. It's very hard to draw like that, okay? I can draw it if I have a ruler. I'm assuming you hand drew this, right?
Yeah.
Okay. Okay, let's check yours. So in the mark scheme, you won't know this, but the mark scheme will give the examiner a range. So the range for the upper limit is at 3.8. It should be between 0.02, which is I think here. This here, 0.02. Yes, 0.02 to 0.24. Yours is not bad, passing right through the middle. So if your line passes through this bracket on the upper end, and then you go to the lower end at 3.5, not around, at exactly 3.5, it should pass between 0.6, very close, to 0.62. So I guess my answer to your is, are they very strict, kinda? Does yours pass? Almost. So a better line could be to just get this one up a bit, like this. What line should it pass? The last point and the third point. Yours was just, okay, let me undo. Yours was just here. But you wouldn't know lah. So just draw what you think is best. Because you can't know the mark scheme, and just practice a bit. I think, okay, let's compare yours and theirs. 1, 2, 3. Okay, 2 below, 2 on top. That makes sense. Yours was here a bit. Okay, so at the old position, 1, 2, 3. You had 3 points on top and 1 point below. Does that make sense? Like you have 1 point, 2 points here, 2 points on top. This is the third point. But only this other point, it cannot balance the other 3 points, which sort of makes sense. So we gotta move this slightly higher so that we have some points beneath the graph. I mean, beneath the line as well. So something like this, we have 1 point, 2 point beneath the graph and 1 point on top of the graph. Okay, now. Okay, let's balance. All right, now we can look for gradient. Oh, wait, you need to draw your worst fit and best fit line. All right, this thing. Worst acceptable straight line, you will take the maximum allowed gradient or minimum allowed gradient. But very important, to pass all error bars. So the trick is to go from left to right or right to left. Let's say I go from left to right. Change color. Take your ruler, start from left side of the first error bar and extend. Go and find the right side of the last error bar. So before you commit to drawing this line, you better make sure that the ruler passes through all the error bar. Got pass. This one, maybe no pass. So maybe I will have to not choose this line, but I'll draw both for you. So this is the minimum acceptable gradient. But this side here is a bit sus because it doesn't pass through the error bar. Let me draw a different color one. Maybe I'll draw orange. Okay, repeat. And go from right to left to draw the maximum gradient. Somewhere here. I mean, I can draw a bit longer. It's not an issue. Okay. So it's either I go from left side to the right side or right side to the left side. This one, I spot an even more painful area. This one totally doesn't touch. Okay, so I'm not going to use this. Number two, since this one barely touches, I can do this technique that I teach all students. Your pencil, right, when you draw, as long as it's a smooth line, it's okay. It's okay to explain. This is your ruler. Your pencil. Can turn your pencil a bit while still staying on the ruler. It's a small cheat, but still okay. So the only way I can cheat this one is to make it a bit thicker lah. But hey, small cheat. Yeah, pass already lah. Okay, or you just roughly try to course adjust the ruler a bit so it looks a bit like this, but it passes through the error bar. So adjust it a bit. Okay, so criterion that we're looking for, it has to pass through the error bar, and the must hang from left to right or right to left. Okay. So you can slightly adjust the gradient a bit. They do allow that slight adjustment. Bring it down a bit, something like this. Okay lah, good enough. Pass all error bars. But they're so close, so finding the gradient is going to be pain. But it's okay. Label the graph. I want to talk about something about graph labeling. Sometimes students label graph here. They go best fit line, worst fit line. And I go like, which line? Don't do this to yourself, can I? So you just take this label and just push it at a point where I can actually tell which line you're labeling. No, you put here like that. Can? Even better if you just draw an arrow out to help us make it very clear. Oh, this is my best fit line. But you don't draw arrow also can lah. You want the graph grid to be as clean as possible. Just put this very close so that the line is obvious. And then for your worst fit line, if I can, I just label down here one. Or if you're scared the examiner eye didn't go there, we shouldn't. They should actually look at both places. I will label up here. Worst fit line, like right on the line, right beside the line. Don't go label in the middle lah. Middle, you cannot even tell which line is which line because they are like too closely touching. Okay. All right. So once we draw this, we can find the gradient. Can you be a bit economical and use the same large triangle? Sure. They are not too picky about this. If you're scared you make mistake, then you draw two triangles. So the whole point here is to have a large enough triangle. Okay. Do you need to show the dotted line? Yes, please. Please show dotted line. Because no dotted line, no marks. And the same paper 3 criterion apply. Help me remember, were you exempted from P3?
Yeah.
Oh, okay. So I cannot assume you know your paper 3 lah. Okay, good. Triangle have to be big, but similar standards from SPM. So make sure it's at least half the length of the hypotenuse. I can stop anywhere, but I think I'll stop at a point where both lines intersect at a reasonable corner, which I think can be here. Okay. All right, carrying on the journey. Okay. Lazy already. Use ruler lah. I think you plotted your 5th and 6th point. Did I? Really? Yeah. Let me check the table again. Quite hard to plot on the screen. 0.66, 0.7. Oh, this is a bit to one side. Hang on. Shouldn't delete that line. Okay. Yeah. 0. 7, 6, which means we need to shift everything. Okay. 7, 6 is here. 4, 4, 5, 3, 9, 3, 9, 1. This one is okay already, right? The 5th point. Which one is wrong? Huh? 6, 6 is 6, 6 is here, right? Is it 6, 6? Oh, 6, 6 is here. What's wrong with me today? Must be the tired. Hey, apologies. And thanks for letting me know. So I need to try to delete it in a way that it doesn't affect the line. Such a privilege to be able to draw on paper, you guys. Okay, so 6, 6 would be 6, 6 is here. 4, 5, 6. You find the gradient now, you tell me the value. You draw your own triangle. 4, 5, 6, 4, 5, 5, 5, 6. Here. Is it okay now? Double check with yours and see. I don't really need to move the purple line because I drew the purple line following the recommendation by the mark scheme. But yes, a plotting error will cost 1 mark. Okay. Is yours like that too? I just need to adjust the green graph. Green graph not cooperating. I need to redraw the green. Is it correct now? You can help me by double checking yours. If it moves it will be harder to pass this one. Third one. 3, 5, 6. Yeah, this is 5, 6. So which means I will need this. Do I adjust the shape? Why is it such a... Okay, is it fixed now? Let me know. Kind of hard to plot this thing. And why can't they let me fix now? Okay, thanks for pointing it out. Double check yours, I double check mine. But... Okay, so back to regular programming. I also came already, but here is your points. Here and here. So you know what to do, right? I'm just gonna, okay, 0.74, 0.7, is it in the middle? We don't want it to be in the middle. I shall assume that it is 6. Because middle point is always plain. Don't want middle point. 0.3.4. By that I mean if I have a middle point, then I cannot round. I have an extra SF and I don't want an extra SF, that's all. So I tend to take corners. There is no argument. A corner is a corner. And you can tell I tend to stick to the axis. So for example, this one, I choose the axis like this so that I can read easily because it's close to y-axis. But the x-axis I already know. So this one on top is 0.111. Wow, no, 15? 0.15. This one, this point here is also 0.15. You don't write also, never mind, but you can always write to help yourself. 3839. 39? No. 36365. 3.865. And this one would be 3.850. Okay. So gradient of best fit. Best fit would be 0.15, 3.865. Gradient of worst fit 0.15, 3.850. You know what I'm doing. Repeat again. Collect the coordinates from down here. I'm doing something that you obviously can't do in the actual exam. Okay, this one is 3.4. So 3.4, 0, 0, 3.400. And the worst fit line is 0.76, and this one is 0.74. I get negative. Yes, I get negative. So once I get all the coordinates, I do the grid migration again, migrating it back here, which is what your eyes should be doing. Okay, flipping to the back, collecting the coordinates and bringing it up front. Okay, let's take our calculator. Soldier on. Divide by 0.64 minus 0.15. This one is negative 0.7. Okay, SF, right? 2 SF, so I can increase 1 SF to 3. And that's how far I want to increase. This one is 2 SF, so this one should also be 2 SF. 850. Okay, divided by 0.76. Please compare answer. 738. This is mine. So if you draw a different triangle, it shouldn't be that far away. Okay.
Miss Lee, what's the range in the mark scheme for this one?
This one, there is no range.
Oh, it should be that specifically.
Nope, just no range.
Oh.
As long as it's negative.
Oh, really? So like anything.
Because if your best fit line is drawn correctly, your gradient should be correct.
Oh, okay.
Since we drew their best fit line based on their range, that means everyone's gradient should be around this one. So the marking criterion is I just need a negative gradient. Okay, with clear substitution of data points. Is my data points clear? Very clear. So as an examiner, what my eyes will go is to the graph and can I see the points on the line? In this case, I can, but don't plot the graph. Okay, so I shouldn't have drawn this X. Yeah, don't plot the graph. Draw the triangle and write the coordinates near the corner of the triangle. Something like this. Don't plot the graph. Don't plot. I always itchy hand plot last time, then my teacher minus my mark. Okay, now don't plot. Your graph should only have 6 plots, nothing else. Okay. So yeah. My suggestion is to, okay, I probably need to adjust this closer a bit. 10.6. So that it passes through the error bar. Okay, this one, jadi lah 5. I need to make it past this one a bit. Okay, not gonna change much, but paranoia. 0.750. Around there, okay? There's no range. What we need is the clear substitution, and the distance between the data points might be at least half the length of the line drawn. So draw the triangle. Okay, so we are not done yet because they say include the absolute uncertainty in your answer. So to find the absolute uncertainty, or the uncertainty in gradient, you will take modulus the gradient of the best fit minus the gradient of the worst fit. So negative 0.788 minus negative 0.750. Teacher, why don't we use the half range method? Because we didn't find the maximum gradient line. We just look for the worst fit line. This is 0.038. And do you need to change to 1 SF? They are not strict about this now. They were strict in the table. They are not strict right now. So Cambridge is notoriously known to be inconsistent. So let me write my answer first. My gradient is negative 0.788 plus minus, okay? I can write this one at 0.038 to maintain the same DP. Or if you're like, no, it must be 1 SF, okay, 0.04, then this one can be minus 0.79, which kind of works because this one up here is 2 SF. So I think this is a better answer. Okay. So to find the uncertainty in gradient, you can either take the worst fit minus the best fit, or you can go and draw a third line now, but I don't want to draw a third line. It's extra work for no extra marks. I very calculative one with the mark scheme. You don't give me mark, I don't want to do it. Okay, so we are doing the first method, gradient of best fit minus gradient of worst fit. Okay, modulus, because it's plus minus anyway. We cannot, if you want to use half the range, then you need to draw 3 lines. So first, there's 1 line you need to draw, second line you need to draw, and best fit. So the reason why I don't do this method is because it's too much work. But if you want to, sure. Weird flex, but okay. All right. So 1 mark is when you find the uncertainty. Here, this method correct 1 mark already. It must show clearly the substitution. And then you find the gradient of the worst fit line. This is to the same mark. This one here is 1 mark. Okay. All right, next, find the y-intercept. So you need to do y equal to mx plus c for your best fit line and your worst fit line. So normally I'll just best fit line. Y equal mx plus c. So the gradient was negative 0.788. Teacher, do I use a coordinate? Yes. Can I repeat the coordinate that I took just now? Sure. Sure, go ahead. Best fit line 0.74, 3.4. 0.74, 3.400 plus c. You find your c. 3.74. I do in speed mode. Let me know if there's error, okay? Worst fit line. Repeat again. I draw a divider for myself. The gradient was negative 0.750. Then I'm going to use the coordinate here, 0.75, 3.4. Where? Okay, 0.75. So it's 3.400, 0.750, 0.75 plus C. Okay. Now you know why I use common numbers, easier to press calculator. It's just a skill that I developed from doing a lot of questions through the years as a student. Now as a lecturer, if I'm teaching your class tuition face-to-face, I'll just let you do the calculation. Okay, here you want to find the uncertainty of C, y-intercept. You can use C if you want to. Okay, so this one will be equal to 3.98 minus 3.96, which will be 0.02. So your answer will be 3.98 plus minus 0.02. Is there a value? Is there a range? Nope. Just gotta show the working. I'll show you the mark scheme here. Y-intercept determined by substitution. Yes, we did substitute into y equal mx plus c. Yes, very clear now. Find the worst fit line using y equal to mx plus c. Uncertainty is the difference between the best fit and the worst fit y-intercept there. So just show the clear working. All right. So use all the calculations that you did, determine the values of mu and r naught, include the absolute uncertainties and appropriate units. Okay, so let me see what part E is. Okay, so we can, this one is calculation. I think we'll do this part first. So now that you have the gradient and y-intercept, we can rewind time and go back to A. From A, gradient was negative mu. All right. And y-intercept was ln r naught. Nah, go. Nah, negative mu ln r naught. Okay. Do we have gradient? Yes. We're going to use negative. So mu is just 0.788. Got unit or not? Sure, I didn't think of units. Okay, now I teach you. You see it's mm? Then we scroll back up. Look at the equation. Use your big brain and think about the equation. If I want e to the power of something, this something here have to be unitless. Which means mu times t must be unitless. If t is mm, what's the unit for mu? -1, no? They can cancel. Okay. Don't panic, don't convert anything. No need, just -1. All right, y-intercept is ln r naught, and this is 3.98 is ln r naught. So r naught is equal to e to the power of 3.98. Calculator. Okay, I get 53.5. I stick to the same SF. They're like, sure, what's the unit for R naught? Very funny. Okay, never mind. We check here. What's the unit for R? S -1. R naught and R should be the same unit, right? No. Based on this equation, both R and R naught must have the same units. How do I know? Well, e to the power of something has no unit, because this whole thing is also unitless. Exponent is like a ratio. It's like a fancy ratio. no unit one. Exponent, ln, all that no unit one. It's a fancy ratio. It's still a ratio. Okay, I'm pretty sure a further maths teacher is cringing inside for me calling it a fancy ratio, but ln, log, no unit. Just like sine theta, no unit. Cos theta, no unit. Theta got unit, cos theta, no unit. Anyway, we got R naught. So this will be S negative. So this question actually, it doesn't really need you to transfer the unit from the gradient. It actually needs you to transfer the unit from the first part of the equation. Okay, where are we now? We are here already. Oh, we need to find absolute uncertainty. Right. Okay, so the uncertainty in mu over mu, percentage uncertainty, will be the uncertainty in gradient over gradient. So the uncertainty in gradient, let's rewind a bit. It was 0.04, 0.79. 0.04 over 0.79 times 0.788. You bring the mu up and multiply. Divide by 0.79 times 0.788. So this was 0.039. I'm just going to put 0.04, okay? So I have my mu now. I can put 7. Actually, job, I put 7.9, right? Okay, my bad. I'm going to change this to 7.9. Don't write two, note to self, do not write two answers. So what am I doing? I'm doing 11 p.m. things. Okay, which is I actually don't need to do this. It's the same. Look, it's the same. 0.04. Okay, not needed. Do you need to show it? No. You don't need to show. It's the same thing because gradient is straight away y-intercept. So I will make a note here. This one is not needed. Not needed. 11 p.m. brain. Okay, that's just me laughing at myself. Okay, this one, you could use half the range. Okay, so I can find the uncertainty in, because the way I look for R naught was e to the power of y-intercept, correct? And my y-intercept is 3.98 plus minus 0.02. So the uncertainty for R naught will be equal to half bracket e to the power of, we take the maximum one first, 3.98 plus 0.02 minus e to the power of 3.98 minus 0.02. Hopefully that makes sense. I'm using the max min method. You want to use the identities? Sure. But I have 11 p.m. break, so I shall just use the lazy method. And it's not too long. Okay? We use identity. Can, but it's a bit like cutting tofu with a chainsaw because you already have the y-intercept and the range. If it's a table, I may consider, but if it's just one value, then it's a bit of a hassle to derive the identity. Okay, so e to the power of 4 minus e to the power of 3.96 divided by 2. 1.07, which is just 1 SF law. So this will be 54 plus minus 1. Where's the 3 mark? I use different color. This one and this one is 1 mark, both of it. Okay. Wait, unit. Bracket -1 bracket S. Unit, correct, is 1 mark. Absolute uncertainty, correct. the method and this one, plus directly copying this one is the other mark. Because the way they think about it is they are testing different skills. Can you use the linearization of graph to find constant, the red color mark? The purple color mark, can you state the unit? The green color mark, can you find the uncertainty? That's why they mark it this way. Which means it's very, some people can get 0-1 because they do it right for one, but they make a mistake for the other one. So if whatever that you get correct is just one side, like you did everything right for gradient, but you did everything wrong for y-intercept, then it's just RIP, okay? Anyway, the last part here for 1 mark, experiment is repeated using different t. Determine t that will give R this much. I say a silent thank you that they are not asking me to find absolute uncertainty. Okay, so I already have mu and R naught. I guess if I want to, I can use, you have two choices. You can either use the top equation or you can use the linearized one. And I will always use the linearized one because it is already processed. If it's already processed, then it's easier to apply. Because it becomes linear, then it's algebra already. Okay, so this one is ln 20.0. Do we have mu? Sure. Copy this one on top. 0.79. We're looking for t plus ln R naught is 54. You can find t. It's always easier to use the linearized equation. But just show the substitution. It's ln 54 divided by 7.
Sorry, Miss Lee, just wondering, because like for my gradient, I got negative 0.756. So I don't know if it's like too far off.
If your coordinates are correct, then it's correct.
Okay.
And your calculation is correct. So as an examiner, I actually have to test every student's gradient. Mine may not be correct. I'm just, look, I'm drawing graph on the computer, man. If anything, I trust your graph more. I'm manually drawing the graph on the computer. It will be better if I key this in on Excel and ask Excel to plot for me. Does that make sense? My table is like, I'm like, okay, whatever. I guess it works. But yeah, I mean, if your coordinates are right and there's no calculation error, then it's fine. It's fine. Because all these no range one. In fact, even if you draw a really bad best fit line, like your best fit line is totally off and then your gradient is totally off, if your methods moving forward are all correct, you don't lose any marks. You lose 1 mark for this one, line of best fit -1, because your best fit is not best fit. So I legit can draw a line like this, and which I'm gonna give you an example. I can even draw a line just totally not. I'll get -1 for best fit line. I'll get -1 for worst fit line. But moving forward, if I triangle this thing properly and I do the thing that I'm supposed to do, I will not lose marks at all moving forward. Because every single mark in paper 5 has an intention, is to see whether you can perform a function. So yes, you cannot draw a best fit line. Too bad, 1 mark is taken away. But are you able to find gradient? Yes. If your number going to be totally wrong, yes, but don't care. Whatever number it is, if it is true to your line, you will get your mark. Because this mark is awarded if student can find gradient. That's why they never even give any answer. They didn't say, oh, the gradient should be around. Sometimes they will give that answer as a guide to the examiner. But this one, they never give them. They didn't say any value also, or any value also, your value. So that's why I would say, unless there's an error on your graph, like just now you can see I plot the graph wrongly, right? So if I plot the graph wrongly just now and I didn't change it, where will I lose mark? I will lose mark here. Plot a graph is a plotting error. So I plot the error, I plot the point wrongly. But was my error bar correct to the point? Yes. So I won't even lose the error bar mark. Although technically speaking, because I plot the point wrongly, so my error bar is sitting at the wrong place. CIE is nice one. They minus the mark that you wrong, and then that's where you lose mark, and then no more.
Oh, okay.
It's like,
Thank you, Wesley.
yeah, because every mark is for different stuff. Like you see this one all for different stuff. This is for you. Can you find the y-intercept? Yes. Can you find the uncertainty for y-intercept? That will be the second mark. This one is just, can you use the constants to find a new t? Which you can. I got 1.26. What do you get? If let's say we use your values.
Okay, I'm just gonna do the calculation.
So if you get around here, if the number is not too strange, like 400 mm, I'm like, wait, what? Your paper is 40 cm. It's not a paper anymore, it's a book.
Oh,
It's not a
actually,
book anymore, it's an encyclopedia. What do you get?
I got 1.26 also for this one, but my values are a bit different.
If it's like something like 1 mm, I'm happy. It's good. It makes sense. A paper is around 1 mm. Great. If you get 126 mm, which is 12.6 cm, then this is a book. It's a kamus. A 12 cm kamus is not a piece of paper. So as long as the value makes sense, can already. And of course, as usual, they will spot check. I like to say spot check your SF. So they have not compounded anyone's SF until here. So the value of T determined to 2 or 3 SF with correct substitution. You see, I show substitution. All they care about, if you go and read the mark scheme later, is just substitution. And correct power of 10, meaning it should be around 1 point something. If you get 1 point something, you're good to go. Okay. There's no ECF, meaning if you make a mistake here, you transfer here, they don't allow part 3, part 4, or D. Okay. And then you just show the working. I mean, I can do this for them, but I don't think it's necessary. I show the substitution. This is good enough. So all they care about is the correct substitution. And that you are aware that the values are not off. So I think the only possibility for students to commit a power of 10 error, they call it POT, right? It's actually conversion error, power of tens. So normally it's related to conversion. The only possible place I could think of is the student itchy hand go change this to meter lah. For whatever reason, you decide to call this meter, and then you never convert this one back to millimeter. Okay, lor, then wrong now. I didn't change the unit because remember I scrolled down and I saw this was mm, and I'm like, okay, I'm happy, I'm keeping the mm. Okay. All right, this one need practice one. If you sit down and do and focus, it's definitely doable in 1 hour and 15 minutes. But if you do together with me, as I talk you through, it takes forever because I have to talk. Okay. So go try. Maybe you can try the other variant of this year. And if you want to, you can send it to me. I'll mark for you. Yeah, that's it. And normally during the marking workshop, I'll be like, this student gets 24 out of 30. And then the whole group be like, Nani? I gave 28. And then I have to go and find which place I minus mark that the examiner don't want to minus mark. And then we have to discuss. So I'm known to be strict. But yeah, the whole idea is just you show them what they want and things should be fine. Okay. All right. Have a good weekend, guys. I'll see you on Monday. Am I seeing you on Monday?
We have another paper on Tuesday.
Okay. It's okay. We can choose to not take Monday off. And then would you prefer to have it on Friday instead? Or just want to discuss amongst yourself and let me know? You can even discuss in the chats now, okay?
Okay, we'll let you know.
Yeah, just let me know. So I assume Monday don't have, I'll make other plans. Cool.
Oh wait, actually,
right.
actually
Yes.
wait. I think it's paper 5 on Tuesday. Let me just check.
Loan.
Oh yeah, it is.
It's paper 5 on Tuesday. Would
Yeah.
you want to have class on Tuesday?
Okay, I'm not sure. I don't mind anything, so up to everybody else.
I think if it's still Monday night, should be fine, I guess.
Okay. Because Tuesday is this paper, right?
Yeah, sorry.
Okay, no problem. I think we'll just do a random question on Tuesday. You can try the other variant from ON21 to practice. All right, see you on Monday then. Take care.
Okay, thank you, Miss
Thank
Lee.
you.
Have a good weekend.
You too.
Thank you,
Take
Miss
care.
Lee.
Bye-bye.
Thank you.
Thank you.
Thank you, Miss
Good
Lee.
night.
Good night.
Bye.